Welcome to ES310 Lesson 17. Today we're going to extend the impulse momentum work we've been doing over the last couple of lessons to some very interesting applications related to fluid flow. We will look at steady flow. We will look at steady flow where the velocity of the flow does not change with time. And we will look at problems involving a changing mass flow where mass is actually added or subtracted from the system. More information about these topics can be found in Hibbeler's Dynamics text, Chapter 15, Sections 8 and 9. So we'll start by looking at steady flow. In steady flow, the volume into the system is equal to the volume out of the system. For all of these systems, we're going to define a control volume. In this case, we have an open volume, which means that mass flows through the system. So the mass may change with time, but the velocities in steady flow do not change with time. So if we start from our impulse momentum equations, we remember back a couple of lessons, we have linear impulse momentum, which says that the impulse, which is the integral of the forces with respect to time, is equal to the change in momentum, in linear momentum. We also have rotational momentum in impulse equations, where the rotational impulse, which is the integral of the moments with respect to time, is equal to the change in angular or rotational momentum. Take the derivatives of both of these equations, we end up with these equations in the orange box. The linear momentum gives us that the sum of the forces is equal to the time derivative of the change in momentum. In this case, since VB and VA are steady in that they don't change with time, the only thing that may change with time is the mass. And so we have the time derivative of the mass times the difference in the velocities. Rotationally, we have similar equations, so we have the sum of the moments being equal to the time rate of change of the mass times our moment part of our momentum. So R crossed with V minus RA crossed with VA. Another way of writing this time rate of change of mass comes about through looking at the density and the velocity of the fluid that is flowing through our system. So the velocity of the fluid gives times the area would give us a volumetric flow rate, which times the density gives us a mass flow rate. So Q here is the volumetric flow rate. Which is typically measured in terms of volume, so meters cubed per time, seconds, or foot cubed per time. So the solution procedure for these types of problems is we begin with looking at identifying the control volume. Now this control volume will have a velocity of fluid coming in and a velocity of fluid going out. These are VA and VB. And these need to be measured from the inertial reference frame. So make sure that you're in a reference frame that's not accelerating in order to define VA and VB. We can then determine dm dt usually through our volumetric flow rate, so density times Q. We look also at the forces acting on the control volume. So generally our control volume is the volume of fluid that's inside of a pipe. And so the pipe itself is applying forces on that volume of fluid. Those are the forces that we're looking at. We also sometimes have the weight of the water or the weight of the fluid, as well as pressure forces at one end or the other. Then we apply our steady flow equations from the previous slide and determine our unknowns. So let's take an example of how this works by looking at this hydrant. The water flow enters the hydrant at C. So we've got water from the main coming into the hydrant here at C. It's going to be moving at some speed Vc. And we're told that there's also a pressure at C of 300 kilopascals. So if we remember back to statics, a pressure is a distributed load, right, of 300 kilopascals, which means that the force due to that pressure is going to be the pressure times the area at C, just to keep that in mind. Alright, then we want to determine the horizontal vertical force reactions and the moment reaction at this fixed support. So we've got some, I'm actually going to draw them in the positive directions. So we've got some force Y, we've got some force X, and we've got some moment M, all at C. And those are the three unknowns that we're looking to define through this problem. The water comes into the hydrant, and we're told that it has a volumetric flow rate of 0.75 meters cubed per second. So we know Q is equal to 0.75 meters cubed per second. And then it's going to leave the hydrant. We've got VB over here, and we've got VA over here, and notice VA is at an angle. We're also told some diameters, right? So the pipe down here is at C is 150 millimeters, and the pipe at A and B are 75 millimeters, and we're also told that it's equally divided. Right, so if 0.75 meters cubed per second comes in, half of that is going to go out VA and the other half is going to go out VB. So, just real quick, based on these diameters, we can write our areas. So the area at A and B is going to equal 0.004418, and the area here at C is going to equal 0.0177. Okay, so let's take a look at, just as a reminder, the equation we're ultimately going to use. So the sum of the forces is going to equal the time derivative of mass A times the velocity A plus the time derivative of mass B times velocity B minus the time derivative of mass C times velocity C. So notice this looks a little bit different from the equation we had previously on the slide, because in this equation right here we only have one entrance and one exit. So we don't have to split those masses in half. Whereas here, we have one entrance and two exits. So now looking at this equation then, we need to identify some things. We need to figure out what these time derivatives of masses are. And we need to figure out what the speeds are in order to figure out what the forces are. And we're going to use these in the two directions, X and Y. And we also, of course, have our rotational and moment equation as well. So let's start with figuring out what dma is. So based on the equation from the previous slide, dma dt is going to equal rho times qa. And qa is half of 0.75 because it was divided equally. So density is given as 1,000. 0.75 divided by 2, so dma is going to be equal to 375. dmb is also equal to that because it was split equally. So this is also dmb dt. And the last one is dmc dt, which is equal to just rho q, which is 750. So we now know DMA, DMB, and DMC. We need to figure out these speeds. All right, so the speed is also related to the flow rate. So the flow rate tells us the volume that's coming in. If we know the cross-sectional area, then we can also find the speed of the flow that's coming in. So VA is equal to VB, once again, because the areas and the flow rates are the same. And we've got the Q over 2, which is the flow rate for VA and VB, divided by the area of VA and VB. And if we plug in our numbers, then we get that this is 84.88. And a similar equation for VC would give us Q over AC, which gives us 42.44. So it's moving slower when it's coming in than it is when it's going out, which has to do with the cross-sectional area that we're looking at in those cases. So we now have the entire right-hand side of this equation. We have numbers for all of those terms. Now we can start looking at the actual sum of forces in the x and the y directions. So let's look at the x first. Sum of forces in the x direction. The only forces in the x direction is Fx. All right. And that then is equal to, we're looking in the x direction, dma dt is 375. VA in the x direction would be VA times x direction would be the cosine of 30, and that would be negative, right, because it's going, these are our positive directions, x and y. All right, so that's the x direction of VA. Then we have plus 375, which is the dmb dt, times VB. All of VB is in the x direction, so VB. We plug in our, and in the c direction there is no x flow because the water's coming straight in. Okay. And so then we get, so we plug in our VA and VB, which are both equal to 84.88, and we get that Fx is equal to 4.26 kilonewtons. Then we do the same thing for the y direction. In the y direction, the forces, there's two forces. So we have Fy, which is the force of the connection with the ground, and we also have this pressure force, which we said was the pressure times AC, and we know the pressure is given to us right here, and AC we found was 0.0177, so that is actually a known number. And then we look at the right hand side, so we've got 375. In the y direction, VA, we get VA sine of 30. And then we get, in the b direction, there is no y, so plus 0. And in the c direction, all of c is in the y direction, so we get plus v dmc is 750. And VC is 42.44. So we plug in our known quantities. We solve for Fy is equal to negative 21 kilonewtons. And the negative sign just means that when we drew it, we just guessed upwards. We guessed wrong. It should be downwards. Now we look at our moment equation. So our rotational one, we have negative dma dt times VA. So now, let's take a look at our moment equation. So the sum of the moments is going to equal the rotational momentum of each of these flows. So the flow at A has an x component and a y component, and both of those are going to create a moment around this bottom point. The flow at B has just a x component that will create a moment, and the flow at C is through the point that we're interested in, so it does not create moments. So let's take a look at the x component of the VA at A. That would give us dma dt. X component of VA would be VA cosine of 30, and the distance through which it's acting, so the perpendicular distance down to C, for the x component would be 650 millimeters, or 0.65 meters. And that is a positive moment. The y part is going to be dma dt times VA sine of 30, and the distance there would be this 250 millimeters, right, moving out from point C. So that's 0.25 meters, and that is a negative moment, so that's minus. And then we do VB, so dmb dt times VB, all of VB, and that distance is the 0.6 or 600 millimeters, and that is also negative. All right, and the only moment acting on this is the actual moment we're trying to solve for. So all of these quantities are known, and we get a moment of negative 5.16 kilonewton meters. Once again, the negative sign just means that it's actually in the opposite direction from how we drew it. The other type of problem that we can solve using these impulse momentum equations, or versions of them, are systems that have variable masses. So systems that are either gaining mass as time goes on or losing mass as time goes on. So a common one that we look at are rockets. So a rocket is being propelled because it's pushing mass out of its bottom, and therefore is moving upwards. So that is an example of a system that is losing mass. A system that would be gaining mass, the one shown here is a scraper that's digging, so it's adding the mass of the dirt that it's picking up. A lot of the examples in the textbook have to do with a chain, so you're lifting a chain off the ground or something of this sort. So the chain is getting heavier because you're lifting it off the ground. So in a system that loses mass, the equation that we're going to be using is this sum of forces acting on the control volume is equal to the mass times the acceleration, right, the time derivative of v, this is just acceleration, minus this VDE times the time derivative of the mass being expelled. VDE is the velocity of the device relative to the ejected mass. So if we're traveling with the ejected mass, we're looking at the device, what is the speed? That is equal to VD plus VE. Now normally we would write VDE is equal to VD minus VE. But these are in opposite directions, right? So if the rocket is going up, the ejected stuff is going down. There will always be in opposite directions, and that's why there's a plus sign there. That's taking into account the opposite directions. ME is the ejected mass. So this is the time derivative of the ejected mass. So how quickly is the ejected mass being pushed out? In a system that's gaining mass, we have a similar equation, except for this is now a plus sign instead of a minus sign, because we're actually gaining mass. So the forces on the control volume is equal to the mass times the acceleration of the control volume, plus this velocity of the device relative to the injected mass, times the time derivative of the mass that's injected. And here we have a minus sign, which is what we would expect from this type of definition, because those two things are moving in the same direction. So let's take a look at an example. As promised, it's a chain example. So the man is pulling a chain. The chain starts in a big pile at the bottom, and he's pulling it upwards with a speed of 0.4 meters per second. And we need to figure out what is the force that he needs to use to do this. And this is going to be as a function of time. So this is adding mass. So we're going to use the equation sum of the forces is equal to mass times the acceleration plus v of the device relative to the injected mass times the time rate of change of the injected mass. So now we need to identify what all of these things is. Well, for one thing, we know that it is being moved at a constant speed. So if it's a constant speed, dv dt is 0, so this term goes away. So we don't have to worry about the mass times acceleration term. So now we're going to look at, so we need to figure out what vdi is, and we need to figure out what this change in mass with respect to time is. So let's start with the vdi. Vdi is equal to vd minus vi. Well, vd is the speed that the device is moving. In this case, the device would be the hook, right? So that is 0.4. vi is the speed that the chain is moving, right? And the chain is not moving. It's sitting stationary on the ground. So this is minus 0. So vdi is actually just 0.4. So that gives us the vdi. Now let's take a look at this dmi dt. So if we write the mass injected, right, so that is the mass of the chain. The mass of the chain is changing with time, right, because as we're moving upwards, we're getting more and more chain. So at any given point, the mass of the chain is going to be this mass per length of the chain, which I'm going to call m prime, because it's not really a mass, right, it's a mass per length. We get m prime times however long the amount of chain is that's currently hanging from the hook. Well, we can figure L, that length, is changing with this v, right? So that's going to be m prime. L is going to be the velocity that it's moving at times the time, gives us the length of the chain. And so mi is a function of time. So dmi dt is simply the derivative of that, which would give us m prime times v. We know m prime, we know v, so that's a known value. So we now have the right-hand side of this equation. Now let's take a look at the left-hand side, the sum of the forces. So if we look at this chain, right, here's our chain. We have force F at the top, that's what we're trying to find, and we have the weight of the chain, mg, hanging from the chain. Now m, again, is this m prime times L. So this weight, right, is going to equal m prime vt times g. And now we're ready to plug everything into this equation. So we have F pulling up minus m prime vtg is equal to vdi, which is 0.4, times m prime v. Solve for f, we get f is equal to m prime is 2, v is 0.4, g is 9.81, t is staying as a variable, plus 0.4 times 2 times 0.4. Or, multiplying all of that out, 7.85 t plus 0.32 is our function. In our final example, we're going to look at a rocket, which is our typical example for a system that is losing mass. So in this rocket system, we're looking at the stage 2 of the rocket, which is part A here. And we're told that it weighs 2,000 pounds when it's empty, and it's got 1,000 pounds of fuel in it initially, which then gets spent. It's launched from the first stage with a velocity of 3,000 miles per hour, which can be translated into 4,400 feet per second. The fuel is consumed at a rate of 50 pounds per second, right? So this is a weight rate, right? We're used to seeing a mass rate. This would be dw dt, right, is 50. So the mass rate, how do we go from weight to mass, we divide by 32.2, so 50 divided by 32.2 would be our mass rate. And this is the mass rate of the ejected, and it's already and the relative velocity, so that's the VDE, is equal to 8,000. Alright, so if we remember back to our equation, we have the sum of the forces is equal to the mass times the acceleration minus the relative speed times the time rate of change of the ejected. We know dm dt, we know VDE, we know the mass. We're asked to find the acceleration, and notice we get to neglect the weight. So the only force that is acting on this thing is our internal forces, right? Because the thrust is internal to our system. So we get 0 is equal to, and we're supposed to be looking at two cases. So we want to find the acceleration right when it starts and the acceleration right before the fuel is gone. So the only difference between those two cases is the overall mass. So at start, the mass is going to be 2,000 plus 1,000, so 3,000. So at the start we get 3,000 times A minus 8,000 times 50 divided by 32.2. And we can solve for A equal to 133.3. And at the end, we're going to have 0 still. Now we've got just the empty stage, so that's 2,000 times A minus 8,000 times 50 divided by 32.2. And we can solve for A equal to 200.